All right, in this video, I'm going to show you how to conduct the sliding friction experiment using the PASCO 850 universal interface, PASCO sensors, and Capstone software. So to start off, go ahead and open up the sliding friction pre-configured Capstone file. And once you've done that, let's go over the materials and make sure we got everything. First couple things you're going to need, obviously, is the 850. And then we're going to have our passport motion sensor. For this experiment, make sure that it is set to the cart mode and not the person mode, because we are tracking smaller objects here. And then we have our passport high resolution force sensor. And we have our Discover friction accessory set here. I have two of the felt trays. So just make sure you have at least a duplicate of one of these three materials. It doesn't matter which one. And then we have 4 sets of cart masses here. And then lastly, a scale, which will be used to measure the masses of each of these trays, as well as the masses. And then lastly, though it's not needed, but you'll see I have a track laid out here. You don't need it for this experiment, but I only used it for this because the motion sensor will mount on the end very cleanly. And this provides a consistent surface on which I'll be performing this experiment. So there will be very little deviation, at least in that variable. So now, to start off, one of the first things you're going to want to do is tie strings around these trays here. And the easiest way to do that is take your string initially and just tie a knot up on one end here so that you get a circular loop. And then the easiest way to, let's see here. There we go. So once you have your loop made from 50 centimeter string here, you're going to take it and just simply thread it through the cart like such. And then take your end of the string here and then put it through the loop and pull. And so now do that with all 3 carts. We'll be ready to go. All right. So to start off, we'll just jump right into procedure 1 here. The first thing we're going to do is I'm going to use the felt for this part of the experiment, as well as for the train and stack variations when I get to it. Make sure I like to set the cart about 10 centimeters from the sensor. And we're going to place our first 2 carts in. Now I've already measured the masses of these masses as well as the tray itself. And once you've done that, you're going to go into data 2 here. Record all the masses of each of the 3 different tray materials. And then I have recorded each of the 4 steps we'll be using to collect our data. This is the 2 masses with the tray, and then here is 4 masses with the tray, 6 masses, and then finally all 8 masses with the tray. I've already entered those values in here. So now we're going to go back to data 1. Let's set our string up there. Now what we're going to do here is hook the string onto the force sensor, but so that there's no tension on the force sensor at all. And then we're going to hit the 0 button. And let's double check our graphs, make sure they're set up correctly. We have force versus time and velocity versus time. Now, for this part of the experiment, I like to use the track here because you can easier visualize how fast you're moving. You can at least gauge in 1 second how many centimeters you've moved. Because the real trick to this experiment is keeping a constant velocity while you're moving. So let's see, I'm going to go ahead and hit record here. And I'm just going to pull this very slowly, try to keep it as straight as possible. And then hit stop. I don't really like that run. So I'm going to delete it and try to get another one. stand over here. So you want to pull this very straight. You don't want the cart going off to one side and getting cockeyed. So we're going to hit the 0 button and hit record. And pull at a very slow, constant speed. I think that looks good. And we'll just scale to fit all our data. So the first thing we want to look at is on our force graph, where the highest peak is, and that's right here. This is where static friction begins to fail, and then we are now working under the coefficient of kinetic friction. So the first thing we want to do is find the max of this graph, which will be this point. Max is 1.68. And then we'll go ahead and enter that in the static friction column here. 1.68 newtons. We'll go back to data 1 here. And then make sure this force graph is selected. Now we're going to use the area select tool. And we just want to find the average force of kinetic friction along this relatively linear region here. We'll turn off those stats. Then we'll toggle these stats on, and we just want the mean. So we got 1.1 is the average kinetic friction over this time period. And then we want to go over to the velocity graph, and we want to make sure we select the area of velocity that corresponds with the area of the force that we're looking at. So put it right about there. And we're going to look at roughly this zone here. Try to get all the data points in there. Okay. And then we will apply the average for this. 0.09. And then we'll enter that value back on data 2. So this was 1.1. And we need to enter the low speed here on this first run, so 0.09. Okay. Now we'll go ahead and reset our tray back to roughly 10 centimeters. And then place 2 more masses. Okay. And we're going to try to pull the cart or the tray at the same speed or velocity that we did on the first run. So we're going to hook that on there, make sure it's not tugging on the string. Data 1. Let's turn all these off. Okay. Hit the 0 button on your high resolution force sensor. Hit record. And we're going to pull very slowly, very straight. All right. This one, it's a little bit harder to see the peak because I did pull quite slowly and as consistently as possible. So let's select the force graph and open up our statistics. We got a max of 2.61, and we'll enter that into the static friction column. Okay. And then let's move that out of the way. And then we will use our area select tool. Once again, just to select, here, let's just look at this. This region looks very, very flat, very good. And we'll turn off those statistics over there. We'll turn these on. We just want the mean, 1.96, and we'll enter that under the kinetic friction. Okay. And same thing, we'll now select the velocity graph and open up our area select tool. And we'll try to select it for roughly the same time length as the force, right about there. Move this legend out of the way. All right, I think we covered all the points in there, great. Let's find the mean. Okay, 0.08, still close to first, and we'll record that. Okay. And next we will do the same thing. Add 2 more masses. Hook your force sensor on there without any force on the string. Okay. Make sure to zero it. To state 1. So hit record. You want to make sure to keep the force sensor as parallel as possible with the. Oh, we had a little error there. Oh, did not get a good recording on that one. Try again there. Let's set to the right. Let's delete that last run there. That was not a very good one. Okay. Zero it again. And hit record. So be able to fit all these. Oh, still not reading it right. What happened there? Motion sensor is good. Let's see why she stopped working. Time. Out. Hit record. Oh, too slow on that one. And as you can see, this one takes a little bit of patience to be consistent because you're relying on your own human error. Or at the mercy of, rather. Hit zero again. And one last time. All right. There we go. Let's see what the average looks like on that. All right, 0.09. 0.09 meters per second. Okay. Let's see, scale to fit all of it, great. Well, actually, go over here, turn on our statistics. Max is 3.99 for the static force. We'll enter that. I say 3.99. 0.9. Oops. Okay. And then go back over here, turn off these statistics. Going to use the area select tool, and we'll select this region right here. And we'll go all the way over here. We just want the mean, 2.84. Okay. And then let's go back over here and reconfirm. There we go. About there. Select all that. And we just want the mean again. Okay, 0.1. We'll enter 0.1 here instead. I forgot to use the area select tool when taking the average of that. So you don't want all of it. Let's see. And last time now, we're going to add the last two masses. Make sure you get them lined up straight, so it'll cause the cart to wreck otherwise. Okay. So again, we're going to set our high resolution force sensor up on the track. Zero our sensor. And then we're going to hit record. All right. We got some funky data at the end there. But that's okay, we won't use it. So we'll go down here, click on our statistics. Max is 5.21. Enter that under the static friction column. And then we'll go back. And then we're going to turn off the statistics so they're not in the way. And then we're going to use the area select tool once again. And this region is very flat. Let's go right there. And we'll get the mean for this, 3.75. Enter that here. Okay. And then lastly, we need to take a look at the velocity over this region here. Whoops. Gotta select that. Go. Mean. Okay, 0.08. Okay. So now we have filled out all the data that we can for the felt tray. Now we need to do the case under high speed movement and observe if there's any changes. To pull these out, order that it'll be the same every run. So now we're going to go back and do the same process, but now we're going to be moving the tray much faster than the low speed runs. So you want to aim for something that's at least about 3 times the speed. So I want to be aiming for at least 0.27 or greater meters per second. And for this one, once again, we're just going to be looking at the kinetic friction because we already have the static friction for all these cases here. All right, so once again, attach the force sensor to the loop, but don't have any tension on the string. All right, we're going to zero that. Now I'm going to try to pull this about 3 times faster and be consistent with each pull. So zero it just to be safe and hit record. Okay. So we did get a little error here from the sensor, but luckily that'll average out. So we will go ahead and do the average velocity. Not fast enough. Try that again. We'll delete that last run there. Okay. Zero the sensor. Use area select tool here and just get the good stuff. All right, 0.35. That looks good. And then we want the force over this window as well. Force was not very constant, but that shouldn't throw our data off too much. 1.31. All right. All right, now we try to, oops, forgot, gotta record that speed in there, 0.35. And let's aim for something in that vicinity on this next run. Place 2 masses back in the frame. Force sensor on the hook. Zero the sensor. And then we're gonna activate one here. Hit record. There we go. Now let's look at the velocity just over this region here. Oh, go. Average. Okay. Actually, let's just get over this more. And do the same thing over here. Average. Point 0.2. All right, so 0.38. And then, what do we say? 2.2. Okay. Reset the trolley. Add 2 more masses. Place force sensor hook on string. I can get it. There we go. Over here, zero the sensor, go back to data one, and hit record. All right. Okay, looks like we're going to be using this region right here. So, here's the mean. And same thing over here, area select tool. You just want this good stuff. Let's apply a mean. Let's redo that a little bit faster. No, not consistent enough with the other two. Zero it. Leave that and try again. Some string. Zero it. Record. Ah, okay. Zoom to fit. There we go. And then we're going to use area select tool again and just look at this region here right after the peak. Right up to there, it looks like. Let's make sure I get all those points. Okay, and we're going to get the mean. Great. Same thing over here. Mean. Okay, 0.34. Much better. All right, enter that up there. And then what was the force again? 3.4. Okay. And lastly, move the part back to the end. Place the last two masses. Right. Okay. Back to data one. Zero the sensor. Hit record. All right. That looks good there. Area select tool. This region. Oops, I don't want to get that. There we go. Where it's most flat. Then we'll go up here. Region. Great. Oops. All right, 0.35 speed and 4.28 velocity or force. Okay. Now that you completed this data table for at least one of the friction trays, you'll go on and answer the questions related to the kinetic coefficient under fast velocity and slow velocity and draw your conclusions from there. And then as for the other two trays, you'll perform the same process with these other two trays as we just did with the felt. I won't repeat it because it is the same process. Then once you've collected these values, you'll go ahead and enter them. Whoops, these are already here. You'll go ahead and take the average of all those values from the data table for fast kinetic coefficient, static, and the regular, and then enter those values for each of the 3 trays here. And once we've done that, we can go on to analysis 2 here, which has us looking at a graph. We have the static friction, the kinetic friction, and then the fast. And so we want to take a curve fit here and see what the slope of this line, which should be linear, but we're choosing proportional. Same thing here. We'll do another curve fit. We'll do proportional. And the slope of these that we're seeing here are the coefficients of friction for each of these cases. And let's select proportional for that one. Nail for that one. Let's see if we can get a linear. Oops. All right. Let's try linear. A little bit lower. Well, we'll do a linear for this one just for demonstration's sake. And this slope here corresponds to, so this 0.178. It's a little bit low, but it's close to the average of these values here. And then it'll ask you to compare the kinetic friction to the fast, and then provide your conclusion answers. Now, procedure 2, we're going to be using 2 of the felt trays here, and we're going to be using 4 pieces in each tray. And we're first going to start with a stacked orientation. So we're going to have these 2 felt trays stacked on top of one another. And we're going to perform a low speed run and measure the resulting kinetic friction and compare it. So go back to data 1. I'm going to make 2 more rows here, actually. So for this, we're just going to be tracking the frictional forces for the stack orientation and the train orientation. We're going to, just like before, hook that on there. We're going to zero our sensor. We're going to hit record. Just a regular low speed run. Okay. And now we're just going to measure the friction. Use an area select tool here. This, we'll choose the flattest region. This looks the best right here. And get our mean. So 4.06. Okay. see. 6 is the average kinetic. And then we're going to get rid of that. And we just want to find the, I want the max, 5.25. We'll enter that here. Now we're going to change our orientation to a train. So these are now, instead of one on top of another, they'll be side by side. So the question being asked here is, will we have more or less friction than the stacked orientation? Or will it be the same? Hook this on. Zero it. Okay. So let's same thing here. Oops. Let's do that. Let's find the max, 5.37. Okay. So once again, very close. Very, very close to the static friction on the stacked version. And let's turn that off. Use our area select tool, and let's just select this most linear flat region in here. I think that's probably the most flat on average. Again, I mean 4.22. We'll enter that data too. So as you can see, there really is not much difference between these two situations. The point it's trying to make is that it doesn't matter the surface area in contact. What matters is the material. And once you've filled out this data, you've gotten the kinetic and static friction for both the stacked and train orientation. Then you have the static and kinetic friction for both the other two. Here it says felt and plastic, but I chose to start with felt. So mine would be cork and plastic. But anyways, for the other two, you'll fill that out and then go through and answer these conclusion questions. With the data you have here, you should be able to. And that's how you perform the sliding friction experiment using the PASCO 850 interface and passport sensors.